you to do. So we're going from air into glass, but then back into air again. Okay. To do these multiple step or like multi material thing, take it a step at a time. So show me with your arm where the normal line is. Normal line is perpendicular to the surface. Okay. Tell your neighbor, does light travel faster in air or glass? Does light travel faster in air or glass? Correct answer is air. Is light going to bend away or towards the normal line? Is light going to bend away or towards the normal line? Okay. If there's any confusion on this refraction, please put your cell phones away and pay attention to this. Okay. It's going slower. It's going slower in glass than it is in air. Okay. Here is the path of no refraction. Straight through. There's no refraction going there. Okay. This isn't their answer. Okay. I'm just setting up the problem here. Okay. My wheelchair is going from the sidewalk into the grass. Slows down. This wheel is going to slow down, is going to get in the grass first, and it's going to slow down first, and therefore it's going to bend towards the normal line. What do I mean by towards the normal line? I'm looking at this line here. I don't care about this above the surface. I care about the normal line in the glass. Towards the normal lines like this, away from the normal lines like that. Okay, not this. That's a reflection that bounces off. Okay, it's refracting towards the normal line. Good with that? Okay, so now when it goes from glass back into the air, normal lines like that, and it's going to bend away from the normal line. Here's the path of no refraction. Okay. Now, here's a special case scenario. If this surface is parallel to this surface, this ray is going to end up being parallel to this ray. Okay, so when it bends back away from the normal line, you guys already know that. Okay, everybody good with that? So, if you were looking, let's say this is a pane of glass. You're looking through a window. Here's your eyeball. Okay. You think you see the object in a straight line path. You think you see the object over here. shifted slightly. Okay. Now, this effect is going to be like the shift is going to be more apparent. Either the thicker the glass, like the thicker the glass window, or how big this angle is that you're looking at. Usually when we look through a window, it's just straight away, just straight on, so there is no shifting. But if you're like trying to look like, oh, like you're trying to look through over to the side through a window, like trying to look at the parking lot, oh, who's over there? That's where you can get the shift from where it looks compared to where it is actually. That makes sense? Okay. Any questions there? Hopefully that cleared up some confusion. My suggestion for this one would be take it a surface at a time. Thumbs up if you have an answer. Have a conversation. Correct answer is? Okay, let's take a step at a time here. Show me with your arm the normal line for this surface. Okay, it's perpendicular. Good with that. The normal line. When it goes from air to glass, it's going to bend away towards the normal line. Towards the normal line. Here's no refraction. Okay, bending towards the normal line. It's going to bend like that. Does that make sense? Questions there. This is the normal line it's bending towards. Okay. Show me, going to this next surface, show me with your arm the normal line. Perpendicular to the surface. Going from glass into air is going to bend away towards the normal line. Away. So here is no refraction. It's bending away from the normal line. Correct answer is D. Okay, dangerous dinosaurs. Good with that? Do you see the difference between this scenario and this scenario? Here, the surfaces were parallel, so the rays ended up being parallel. Here, definitely was not the case. Okay. You see how much the ray deviates off of the straight line path. Here, it doesn't deviate that much. It's like boop, boop. Okay. This is like, whoa. A pretty big turn here. When white light makes some crazy big refractions, changes in direction, what happens is it causes the white light to separate into the different frequencies of light, different wavelengths of light. You get a rainbow. Okay, and this is what I was going for on the lab yesterday, where I said take it to the critical angle and then back it up just a tad bit and look at the white piece of paper. Hopefully you saw a color spectrum, a rainbow. Tomorrow we'll get an opportunity if you okay. This is known as dispersion. Okay, is when you take white light and you separate it out into the colors due to refraction. So dispersion, when white light is separated into the color spectrum due to refraction. Okay. When does dispersion occur? When there is a lot of refraction. When there's a lot of refraction. Okay. Secondary question. Oops. What color has the least angle of deviation and which color has the greatest angle of deviation? Which one has the least? Which one's bent the least? Red. And which one's bent the most? Violet. Okay. The reason that is because of the different wavelengths. Hey. Yeah. Okay. So, oops, wrong way. Which one has the least? Red, because it has a longer wavelength. The longer the wavelength, the less it's affected by refraction. The shorter the wavelength, the more it's affected by refraction. Do that. Yep. So here, different wavelengths are affected differently. So the longer the wavelength, the less it's refracted. The shorter the wavelength, the more it's refracted, the more it's bent. Okay. So where do we see this? Obviously rainbows. Okay. Okay. So what do you need? What are the necessary ingredients in order to see a rainbow? Water, light, and eyeballs. Okay. Now, here is how this goes down. So white light from the sun goes from air into water in a raindrop. Okay. It refracts one time. Okay. Most of the light gets out, but some of the light is reflected back in. Okay. And it refracts again. This is enough to cause white light to disperse into the color spectrum. Okay. If you look, this is a picture of a green laser going through a raindrop, and most of the light gets out. Some of the light is reflected back. This is the amount of light contribute, like the percentage of light, the intensity of light that forms a rainbow. Not much. Okay, and this is why we don't see a rainbow often, because it has to have a lot of light in order for us to perceive a rainbow. Okay, Ben, excellent question. That's coming up in 3 minutes. Okay, now each raindrop spits out an entire color spectrum, whole thing, red, orange, yellow, green, blue, purple. Okay, if you can remember what color is on top on a rainbow? Red, and on bottom, purple, violet. Okay, notice which one's getting bent the most. Purple. It's on top. How does we just okay? Here's the deal. In order for you to see a color, see anything for that matter, light has to get into your eyes. Okay? This raindrop, so rain's falling, okay? This raindrop has the whole color spectrum coming out. Red, orange, yellow, green, blue, blue, purple, whatever, okay? Purple is hitting your forehead. This raindrop is shooting red into your eye. So you see red from this one. You don't see anything, you don't see purple from this raindrop. This raindrop at this moment in time is right here lined up so that purple goes into your eye. Red's hitting your chin. Okay, so you see purple. And then all the other colors in between here are what cause you to see the different colors. So red ends up on top, purple's on bottom. Is it possible to see a rainbow upside down? Nope. Yep. That's why. Okay. So, um, let's say it rains, the sun comes out, you're like, oh, the conditions are ripe for a rainbow, and you start looking around like, where's that rainbow? Here's where to look always. Find the sun. Find the sun. Put your back to the sun and look away from the sun. There's the rainbow. Okay. The sun will always be behind you because sunlight comes in, bounces off, and into your eyes. Good with that? Correct answer is whenever the sun is near the horizon. The sun has to be at your back. At the noon time, the sun is up here. The only place you're going to see a rainbow is if you are looking down and you have your like hose, your sprinkler, like you'll see a rainbow below you. where the sun's behind you. Does that make sense? So the only time you'll see a rainbow in the sky is when the sun's at the horizons in the morning or in the evening. The lower it is on the horizon, the higher it will be in the sky. Good with that? Okay. Turns out that each raindrop is actually spitting out a cone of light, not just a band, but like a, and so we see that as a cone. So we're seeing into like a cross section of a cone, like looking through like a megaphone type thing. Does that make sense? Okay. What would happen if you walked towards the rainbow? Well, you would see the red would be shooting light into your eye from these raindrops now, and purple or blue from these raindrops. So as you walk, it just moves with you. Does that make sense? So the leprechaun's like, stupid kids. I'm gonna run real fast. Like it just keeps moving with you. They got another trick up their sleeves. Rainbows are complete circles. Just the earth gets in the way. So like the end of a circle. There is none. Stupid kid. Okay. And the only way you can see it as a full circle is if you're at an elevated point of view. Or taking the garden hose during noontime in spring, you can see most of it. You can see most of it. Okay. Good at that? I know, right? No quick, get rich quick schemes. Oh, that's another great question. I'm going to have to postpone that one. It's nothing to do with the ocean. But we will get to that. It was part of the lesson, but we will run out of time. Maddox. No. Maybe a little bit, but no. Yep. Okay, so Ben, here's your double rainbow. It's just the stuff that's in there. Okay, so double rainbow occurs. Here's the geometry for a single rainbow. Okay, a double rainbow, light comes in and bounces twice before getting out. Okay, now notice the order of the color spectrum coming out normally. Double rainbow. Okay, it's flipped. So if you ever see a double rainbow, the primary rainbow is going to be red's going to be on top, purple's on bottom. It's inverted for a secondary rainbow. Great question. The question was, how does the water bounce twice? So the sunlight always does this. Anytime you get the sun out, regardless if you see a rainbow or not, it's doing this geometry. It's just not bright enough to see a rainbow. So it's doing the primary rainbow and the secondary rainbow. It just takes a whole lot of sunlight in order for us to see this. It's like being far away from someone and you can't hear them. The intensity isn't strong enough for us to hear it. Okay, Caitlin. How do sundogs work when they're like 100%? Great question. Next slide. CJ. Is there like a specific season that you would be more likely to see a double rainbow because we're closer to the sun? No. It's more of I've seen double rainbows when it's been less humid, like conditions that are less have less humidity. Well, that's not true. I've seen them in Hawaii. It's just if the storm fronts, like if the sun can come out fully, or like if the storm clouds are more isolated here in the Midwest, storm clouds are just blankets. In other places, um, where they're more isolated. Like you get like here's a thundercloud, and it's raining here, but not over here. Sun can get through. You get a whole lot more intense sun rays. Okay. All right. So sundogs. These are also due to refraction, but this is a different geometry because of their ice crystals. So you'll see these in the fall or the winter time when it's colder. Um, like you'll see, I've seen these frequently in the sky, and you actually look towards the sun to see these. No, completely different than northern lights. That's those are the ions from the sun get trapped in our magnetic field. Okay. What? Oh yeah, they're ice crystals. So, like in the fall time, just look in the sky in the fall or the winter, cold. Okay. All right. Mirage. We can make this. We can do this. Here we go. Ready? So you open the oven, or you open the car door on a hot sunny day, or you look over the asphalt parking lot or the roof, and you see heat waves. Everybody know what I'm talking about? Okay. That's due to refraction. Okay. Light travels faster through hot air than cold air because it's less dense, and that causes light to bend. Okay, and that's what causes the ripples. You okay with that? So that's refraction. Now, if you have a crazy strong, uh, well, mirage is also a consequence of refraction. Okay, this is where you're like driving and it's on a hot day and you see puddles in the road, and then by the time you get to it, they're like all dried up. And you're like, wow, it's super hot. They must have evaporated. No, it's a mirage. Okay, here's how this works. So, quick disclaimer: this tree would be like a mile away. Okay, it's just really squished. The air near the surface, sand or asphalt, super hot, and it cools down as you go away from that. Light coming off of this tree is going to go through different temperatures, different densities of the air, and so it's going to cause it's going to speed up and bend away from the normal line. At some point, totally internally reflect, and then go up into your eyes. You think you see light going in a straight line path, so you think you see the image or you see the palm tree down here upside down, just as you would see a reflection off of water. Okay, so here, this isn't a really great picture, but I like it because the headlight light would be hitting this part of the street, but it being bent up, and you think you see an image right there. Okay, so here's some pictures of mirages, actual mirages in the desert.
Oh no.
See ya.